Oh, hey, Unit 3, Oceans. With this unit, we will be using your textbook a little bit, portions of Chapter 19, 22, and also 24. Oceanography is defined as the scientific study of the ocean, and it uses all the branches of sciences, so chemistry, biology, physics, geology, and other sciences. Huge, all-encompassing. What oftentimes happens is that you will have an oceanographer that is primarily focusing on chemistry, or an oceanographer that's primarily focusing on whale populations and their migration. So even though it's all under the title of oceanography, there are branches within the oceanography, and they all work and interconnect with one another. So what are the instruments that oceanographers use? Well, in order to learn more about the deep sea, we have deep submersible vehicles. And these are very similar to like a space shuttle, you know, because there's extreme environment in both situations. So they have to be able to withstand high pressures. We have ships that contain deep sea cores so that they take a sampling of the sediment, and then we can learn a little bit about historical events based on the findings there. We have sampling tools for water, like salinity and temperature, pH, nitrogen, all of those things, depth measurement tools, so radar to measure how deep the area is, sonar as well. Robotic mini subs exist. They may not house people, they're mini, but they will allow us access to get our instruments down to these areas that are quite remote and people can't go. We also, surprisingly enough, use satellites a lot to actually find out what's going on in real time with our oceans. When we have a tsunami event, major energy causing earthquake under the ocean, causing a massive wave, we can actually sense that as soon as it happens. It's relayed, that information is relayed from buoys, floating buoys, that send that radiation to the satellite. The satellite sends it back down to our Earth, and so we have scientists constantly monitoring that, which is pretty awesome. But not just that, we also can look at sea surface temperatures using the infrared sensors for measuring that. Can measure water vapor motion and just a lot of different things you'll see. In fact, you'll see some of those images later. Moored buoys. Moored means attached. Buoys is a floating device, and these things they're floating buoys, but they are attached by a string to the bottom of the ocean, and on that string, that attachment, are all kinds of instruments and sensors. On the buoy itself, there is the means to send that information up to satellite. So all of our moored buoys have the ability to relay information up to the satellite that's in orbit around our planet, and then that satellite relays that information back down to Earth to computers. Computer models also allow oceanographers to enter in some data that has been collected and allows them to then predict what's going to be happening. Things like, you know, El Niños and La Niñas, if you know anything about those there's signs that are being shown. There's data that can be collected that will help point in the direction that one of those events might be happening or not. Right here is an image showing a deep submersible vehicle with humans in there. It's all lit up and it's equipped with all kinds of equipment. And then here's an image of a satellite. So we would have these moored buoys somewhere down here in the ocean, and they would send the signal up to the satellite. The satellite would then send the signal anywhere on the planet. And if you are a scientist and you're interested in collecting some information, you know, especially even NASA or NOAA, that information is available. Some definitions. Ocean current is any continuous flow of water along a broad path in the ocean. With our lab, we did motion in the ocean. We called it motion in the ocean. And motion in the ocean, that really is a current. So an ocean current can be defined as surface, or not defined, but it can be in the category of surface or deep ocean currents. So deep ocean currents are going to be driven by gravity and differences in density. More dense will drop down, less dense will rise up. Surface currents will flow in the upper 1,000 meters of the ocean, and they are driven by a variety of items. Think of your motion in the ocean lab in all 4 different stations. You know, all of those are influences on surface currents. This little link will show us pictures of the global surface currents, so just hang in for just a second. Okay, that's not it. Surface currents are primarily driven by wind. That is the main driving force that pushes the currents in a particular direction. And there's a great image that I'll show you guys. It's also in your book on page 532, but I'll show you guys in class surface currents maps. And they're all over the place. They do follow a particular pattern based on the Coriolis effect, which was one of your stations in the ocean lab. In the northern hemisphere, the fluids, including the air and the ocean, will flow clockwise. And that's because in the northern hemisphere, the planet itself is moving counterclockwise. So all the fluids, you need to remember that all the fluids flow clockwise in the northern hemisphere. In the southern hemisphere, it's counterclockwise. And then also there is a temperature pattern of the currents that shows up. So if any current is moving away from the equator, it's going to be a warm current because it had picked up energy at the equator. The equator receives the most sunlight energy on our planet. If there are currents that are moving toward the equator, they are cold. They're coming from the polar region where they had to, where the energy dissipated to the environment in the atmosphere. So they're cold. They get less sunlight energy. This next slide is just a list, and I don't think I have you writing this down at all, but this is a list of the major causes of the surface, primarily the surface, and then we also have deep water currents that are caused by some of these as well. So we'll look at each of these individually, but here's just the list of them all. Wind, Coriolis effect, unequal heating of the earth, temperature differences, salinity differences, and both temperature and salinity will cause density differences. So recognize wind, Coriolis, temperature, and salinity as stations in the motion in the ocean lab. Unequal heating of the earth I'm going to demonstrate for you guys, and density differences ties in with these two. So there you go. Let's start with wind. There's 2 sets of prevailing winds that form most of the ocean currents. We have the trade winds and the westerlies. Maybe you've heard of the trades. I'm not sure, but trade winds and westerlies. The trade winds, and there's a great diagram on page 533, but the trade winds blow from the northeast in the northern hemisphere, and they blow from the southeast in the southern hemisphere. Mostly, I just want you to get this down in the notes. I am going to show you a map, and we're going to show you where those wind patterns occur. But what they do is they'll push the north equatorial current westwards. It pushes it to the west. Now the westerlies are named for where they're coming from, and so they're blowing from the southwest in the northern hemisphere and the northwest in the southern hemisphere. So they're from the west. Trade winds are from the east. So trade winds are also called the easterlies as well. So we have the easterlies and westerlies. I will refer to them as the trade winds primarily. But anyways, the westerlies are what flow over our area, our latitude, Portage, Michigan. The westerlies. They also push the North Atlantic drift eastward, delivering the warm temperature of that current to the east side of the Atlantic. I've got some great clips that I'm going to show you guys in class. Coriolis effect is a tendency of an object moving freely over the Earth's surface, like wind or ocean currents, to curve away from its path of travel. You guys, we're on an object, the Earth. We're on a rock. It happens to be rotating. Because of the rotation and the fact that we're on a round object, we end up with this Coriolis effect. So there's a curving that occurs, and the oceans show that curve in respect to the Coriolis effect. So I have another clip I'm going to show you in class, but you're going to notice that in the northern hemisphere on any map, if you look at the Atlantic Ocean in the northern hemisphere, you're going to see it go clockwise. There's a pattern, there's a path. It's like a circle. It makes a little circle, a clockwise circle. Same ocean in the southern hemisphere is going counterclockwise. And this is because of the Coriolis effect, my friends. The last slide, unequal heating of the Earth. In this image right here, you see that we have the sun and the Earth is in two different positions. This is going to be winter in the southern hemisphere or northern hemisphere. This right here is representing summer in the northern hemisphere, and the sun is right here. You can already see that there's a more direct hit in the equator area. If you're looking at the angle of these lines, it's more direct. Up here at the poles, there's a much smaller angle right here. Maybe if I extend this line to hit that pole, much smaller angle, and so therefore the heat delivery doesn't deliver heat the same way here at the poles, the same way it does at the equator because of that angle. So we have more heat delivered at our equator region, no matter what season it is, and we have less heat being delivered at the polar regions, and this is the same for the South Pole as well. So it's unequal. So more direct rays equals more heating. This occurs between the latitudes of 23.5 degrees north and 23.5 degrees south. So right here, these two lines, this band right here is the band on our planet that gets the most energy. Anything above that or below that band is going to get less. This would be between what's called the Tropic of Cancer and Tropic of Capricorn. Less direct sun rays equals less heating, and those are the polar regions. And currents will transport heat from the equator to the cooler poles. You're going to notice that warm currents tend to run from the equator up, and then they cool off as that energy is transmitted out into the environment. They cool off, and they're not getting much energy coming in, so they stay cool. Cold water is then going to move along south, in this case toward the equator. So anytime you see a current going toward the equator, it's going to be cold because it's coming from the polar region. And there's another little video clip that I'll show you in class, and that is it for this segment. This is segment 1, unit 3. Done.